everybody. Usually you see the math lesson screen up here. This morning I wanted to start off by talking about, in the updates I'll always have the Google Meet codes. You guys have always found that, and then the assignment for the day. This link to the daily calendar for pre-calculus, that's been there for a while, and that is the exact same daily calendar that's posted in Schoology. But I've got a new one down here, and that's a link to the PDFs of the pre-calculus textbook. Apparently, Adobe Flash is mad that they are not receiving royalties from book publishers that use Adobe Flash for their products. And so they have pulled it away. They took their toy and they grabbed it and they left. And so sometimes you'll go to try to use the pre-calculus textbook and it'll tell you that you can't. And if that's the case, somebody at the district office went ahead and made copies of all the pages, each individual page in the pre-calculus book, if you can believe it. And so now there's a link down here to the PDFs of the pre-calculus textbook. So just so you know, there's a backup in case you're trying to use the pre-calc textbook and it won't work. Again, it's all about money. Adobe Flash says you're using our product, and for that you should pay us, and the book publishers said no, so they're in a fight. Eventually Adobe Flash will probably get their money, but we've just got to work our way through this. What a time for it to happen, right? But that's how it works. So 3.5, we are going to be reviewing solving exponential equations algebraically and graphically, things that we did in Algebra 2, but obviously the problems are going to be a little bit more difficult at the pre-calculus level. We might get to solving some of the logarithmic equations algebraically and graphically today, but tomorrow we'll be doing applying Newton's law of cooling, so doing the application problems. And we'll talk a little bit about the modeling and the regression models. But we're truly getting to the point where when we have data, we should be able to put that in our graphing calculator, take a look at the scatter plot and say, oh, that looks like, and then use that regression model in order to get the best model possible for what we're doing. So yesterday, just to give us a little bit more time, I went through and already did a couple of pretty basic solving exponential equations by getting common bases, and that was these two right here. And again, we have to recognize when we see 9 and 27 that those are both powers of a base of 3. And when we see numbers like 1/2 and 1/4, we have to recognize that those are base 2 powers. So you kind of have to change your thinking a little bit when you get to these problems, because you have to think about that common base and you have to think in terms of powers. Now, C is definitely more difficult. So this is an extension problem. That means this is building off of what we've already done. And there's a hint here to use a base of 2. So I look at all of the numbers that I see in this problem that would have to do with being a base. And I realize, well, that's not a problem for 1/4, because that's 2 to the negative 2. I mean, we get the fraction by a reciprocal, which is negative, and 2 squared is 4. 16, that's 2 to the 4th. So that's not going to be an issue. 8 is 2 to the 3rd, and then we have 2 to the 1st right here. So I just have to keep track of all the other stuff that's going on in this problem. So let's go through and change to those bases of 2. 1/4, of course, is 2 to the negative 2nd. And then we would have the cubed root of 2 to the 4th, but all of that is raised to the x plus 4 power. And then, as we move to the right side of the equation, we have the 5th root of 2 to the 3rd over 2, all raised to the 2x minus 1. So the danger with this problem is really that we're going to lose something because there's so much to keep track of. And we've talked before about how when you have radicals with different indices, this one has an index of 3 and this one has an index of 5, best option is to go to fraction powers. And so that would be the next step for us, would be to change this 2 to the 4th and the cubed root to the 1/3 power. So that we can start working with the fraction powers instead. And on the opposite side, we do the same thing with that fifth root of 2 to the third. So it would be 2 to the third to the 1/5 power over 2, all to the 2x minus 1. Well, now I can see that the next step would be raising a power to a power, which means that we have to multiply. So we'll have 2 to the negative 2 still sitting out in front. I probably should put parentheses there. But 4 times 1/3 will be 4/3. And on the other side, 2 to the third raised to the 1/5 power will be 2 to the 3/5. So now I think about my next step, and I realize basically my parentheses are done here, except for the fact that inside these parentheses on the right, I still could do some subtraction, and that's because division in exponential language, our properties say division is subtraction. So 2 to the negative 2 times 2 to the 4/3 raised to the x plus 4 power equals, and then 3/5 minus 1 would be 3/5 minus 5, oh, and then I put a 2, minus 5/5. There we go, that's better. And 3/5 minus 5/5 would be a negative 2/5. Now we're getting somewhere. And I still have powers being raised to powers. So again, that means I'm going to have to multiply. I have to distribute. So my little 2 to the negative 2 is still sitting here waiting for the rest of this to get simplified. And this is going to be 4/3 times x, which is going to be 4/3 x. And then 4/3 times 4 will be 16/3. And then on the other side, we have to distribute that negative 2/5. So negative 2/5 times 2 will be negative 4/5. Remember, I keep thinking you guys are wondering, how am I getting this stuff so fast? Remember, just do the 2 over 1, and then do top times top, bottom times bottom, and it's not going to be an issue for you. And then negative 2/5 times negative 1 is plus 2/5. So negative 4/5 x plus 2/5. Now before I get going anymore, I'm going to double check all of my exponents here. All right, so far so good. Left-hand side, multiplication taking place. I'm really just following the order of operations. It's just that this is a really involved problem. So on the left-hand side, when we multiply similar bases, we add the exponents. So I'm going to have to take this negative 2 and add that to 16/3. So I want to think about negative 2 in terms of thirds, and that would be a negative 6/3. So it'll be 2 to the 4/3 x, and then negative 6/3 plus 16/3 would be 10/3. And then we still have the other side. So finally, we get to the point where we were really doing this math yesterday, where we said, okay, the bases of 2, they're the same. That's not what I have to make sure is equal so that this statement is true. What I have to make sure is equal is that the exponents would end up being the same. So now I can drop those bases of 2 because they're already equal. And so this becomes kind of, I guess I'm thinking it's like an algebra problem within an algebra problem. Because now we need to solve when we have quotients. And how we figured out the easiest way to do that is to always go ahead and multiply everything by the LCD. So our LCD for 3 and 5 would be 15. So we'll multiply every term by 15. And we're really just following the property of algebra that says as long as you multiply by the same thing on both sides, you'll be just fine. So here, the 3 and the 5, we'll do a little bit of division, and we'll get 5 times 4, which is 20x. A little bit of canceling here with the 3 and the 5. Again, we'll get a 5, so that'll be 5 times 10, which is 50. On the other side, when we do our division with the 15 and the 5, we'll get a 3. So negative 12x plus 6. Now it's looking a lot better. So we go ahead and add 12x to both sides. And we might as well subtract the 50 while we're there. So 32x equals negative 44. We divide both sides by 32. And do a little reducing because 4 will go into both of those. Phew. I love this problem. I mean, when you look at this and you realize how much work we had to do with the bases to get those to be the same, and our review of all of the properties of exponents that we have, and finally we have the bases that are going to be equal, so we can drop those, and it becomes a problem about solving an inequality or an equality that has quotients in it. So, wow, rational equation, big stuff. But that really shows a lot of the learning that you did in Algebra 2 last year about, using those properties of exponents. Most people, that chapter, it's chapter 6. Most people remember chapter 6 as the toughest chapter that they had in Algebra 2 because there's so many rules that we have for properties of exponents. And logarithms use those same rules. So now, this says we're going to solve the exponential equations algebraically. And if your packet doesn't say natural logarithm, write that in there up at the top. I think, yeah, this was when I was sick the first time. I think Mr. Bloom ran these off, and it still just said logarithm. But again, we have to get used to using the natural logarithm. In calculus, you're going to use that a lot. So the method that we're going to use is taking the natural logarithm of both sides and expanding. Now, we can only do that when the base is exposed. What I mean by that is, in this first problem, you can see the base of 3, it's right there. There's nothing in front of it. There's nothing on that side that we have to get rid of. So it's already isolated and exposed. But with E, we're going to have to do some manipulation first, some algebra to get that out of there. So for D, we're going to take the natural logarithm of both sides, which seems kind of counterintuitive because, the easiest way to solve this problem would be to take logarithm base 3 of both sides. But again, we have to get more practice with natural log. And then I remember that exponents are supposed to become multiplication in the language of logarithms. And now if I want x all by itself, I'll have to divide both sides by the natural log of 3. And then we'd grab a calculator and figure out the natural log of 11 divided by the natural log of 3. Oops. Natural log divided by natural log of 3. So 2.183 to 3 decimal places. When you get to college, they still do hold with a 10,000th position because we're getting you ready, most of you anyway, because most of our class is going to be sophomores and juniors. We're getting you ready for the AP exam. We do the 3 decimal places. But historically, logarithms are usually solved to 4 decimal places, but we'll stop at the 3. All right, like I said, for E, that one's not ready to go. That one we have to divide both sides by 9. And of course we can do a little reducing because 3 goes into both of those. And then we think about the method, which is using natural logarithm, and that works out fantastic on this problem because the natural logarithm and E, those are inverses of each other, so that's going to be gone. And then we just divide both sides by 2. Now notice, I don't stop and figure out what the natural log of 10/3 is, write that down as a decimal, and then divide the whole thing by 2, because that could introduce a rounding error. We don't want to do any of that. What we want to do is wait until the very end when we have a perfect answer, and then punch it into the calculator. Now, I'm not going to make you watch me punch a whole bunch of these into the calculator anymore here, but this one has a fraction in there, so maybe I'll punch this one in. Natural log of 10/3. Divided by 2. So 0.602. And you may have noticed I used parentheses for the numerator. And that's just my policy of better safe than sorry. I want to make sure that the calculator knows order of operations, find the natural logarithm of 10/3 first, then divide that answer by 2 and see what you get. Alrighty, F. So with F, the bases are exposed, but things are kind of weird. So natural logarithm, because the bases are exposed and isolated. But then we think, well, that's a big mess. How am I supposed to get anything out of that? Well, we have to follow the properties of logarithms, which say that if you have an exponent, that's multiplication. So this x minus 5 is going to come out in front as multiplication, and this 3x plus 4 will come out in front for multiplication. Now, in order for me to solve for x, I have to be able to isolate x. In order to be able to isolate x, I'm going to need all the x's on one side. But I can't do that unless I do this multiplication first. So I do have to distribute. So it'll be x, natural log of 7, minus 5, natural log of 7, equals 3x, natural log of 2, plus 4, natural log of 2. Well, now I can move my x's on the same side. And it's totally up to you which way you go. I guess I will subtract x natural log of 7 from both sides. And then I suppose you could move over that 4 natural log of 2. You could have done that in the same step. But there's a lot to keep track of here, so when you try to do too much at one time, you start to have problems and you start to lose things. All right, so far so good. Now, I have these are actually just numbers on the left. This is calculator work on the left. But on the right, I have my x terms all on one side now. And I think, okay, how am I going to get x by itself? Well, the only way to separate it from all this logarithm business is to factor it out. So we're going to have to factor out an x over there. Looks like so. And then, to get the x by itself, we're going to have to divide both sides by 3 natural log of 2 minus the natural log of 7. All right, so we're going to have a beauty to punch in this time. Still need more room. Alrighty, so negative 5 natural log of 7 minus 4 natural log of 2 divided by 3 natural log of 2 minus the natural log of 7. And you definitely use parentheses on this one if you wanted to punch it all in at one time, because you need the calculator to know, do everything in the numerator, do everything in the denominator, and then do the division. And this one comes out to, I probably better punch this one in too. I keep thinking I don't want you to have to watch me do all this punching in, but these are pretty involved. So, all right, we've got negative 5 natural log of 7 minus 4 natural log of 2 finish off that second set of parentheses divided by parentheses 3 natural log of 2 minus natural log of 7. And finish off the second set of parentheses. And there's our answer. So to 3 decimal places, negative 93.627. So again, it's getting involved because we're using natural log to try to solve, and natural logarithm, the base of e doesn't match the bases that we have, so we're not seeing those inverses. But this is giving us some fantastic practice for manipulating with e and natural logarithm later on for you. Alrighty, this little bugger right here. Oh, well, I could do natural logarithm if I didn't have all that mess going on in front. Well, notice how we have the 3 and we have the 4. Now, we're not going to be able to get rid of both of them. You know, if I could divide both sides by 3, it's not going to work out nice. If I could divide both sides by 4, it's not going to work out nice. So what you do is you just decide, okay, which side do I want that on? And I'm just going to divide by 3. I'm also going to change that 1 plus x to x plus 1 because that drives me nuts when those are backwards like that. So I've divided out the 3. And now I do have one of the bases isolated. And again, that's really important if we're going to be using natural logarithm. So I'll take natural log of both sides. Now, over here, that means I have to break up that multiplication. So multiplication in logarithm language is addition. So it'll be the natural log of 4/3 plus the natural log of 6 to the x plus 1 power. Now I have to bring those exponents down in front and make those multiplication. And now, feeling a lot like the last problem. So I remember in the last problem, I had to do my distributing because that was the only way to get my x's on one side so that I could isolate it. So it's going to be the same thing here. We have to distribute first. Like so. All right. Now we need everything with an x on one side and everything that's just numerical that we could punch into the calculator on the other. So we'll want to subtract x natural log 6 from both sides. And I'm going to go ahead and do 2 steps at once here. since we already did one of these. So on the left-hand side, we have 2x natural log of 5 minus x natural log of 6. And on the right-hand side, natural log of 4/3 plus natural log of 6 plus natural log of 5. All right, got to get that x all by itself. Same thing as last time. Remember, we're trying to make those connections to things we've learned previously. So we'll take out the x by factoring. And then we'll divide by 2 natural log of 5 minus natural log of 6. And of course, that will cancel out on the left-hand side and just give us x. And then we have this monster left to punch in. And again, it's just a lot of punching in at this point. I mean, these are all numbers. The calculator has that natural log information completely stored for us inside there. So I'm not going to punch this one in and make you watch me do that again. You can see you need the parentheses for the numerator and the denominator because the calculator needs to know, do all of this on the top first, then all of this on the bottom, and then do the division. And this one works out to be 2.585. Now, perhaps somebody is thinking, well, Cedar Home, couldn't we make this easier to punch it in by condensing? You know, condense the numerator and condense the denominator? We could, but remember, the more steps that you do by hand, there's more chance that you would make a mistake. So it's actually safer to just stop here and say, you know what, I'm just going to punch this in with the double parentheses. We could, if you do it right, you'll be just fine because we know that addition in logarithm language is multiplication. So you could take 4/3 times 6 times 5, get an answer, and you could put this 2 back up here and make this 25. And then we'd have division by 6, so that would be natural log of 25/6. But again, there's a lot of room for error when you do that. So better to turn it over to the graphing calculator and let it give you the decimal there. This is a perfect answer as it is. It's just that we have to see the decimal answers when we talk about logarithms. So there's the second method. That was the big one there, taking natural logarithm and using that to solve. And here's a third method, using factoring, solving quadratics techniques. So they're saying we're going to be able to solve this a lot like we would solve parabolas. Quadratics are parabolas. So let's take a look at this. All right, for h, interesting. Okay, but we've got an x down there in the denominator, and we're never supposed to have what we're trying to solve for in the denominator. So probably the easiest thing to do with this one would be to slap a 1 underneath that 5 and then just cross multiply. All right, well, obviously I'm going to have to distribute the 5 because, again, I look at that x and I realize eventually I have to have all my x's on one side. So 5e to the x minus 5 equals e to the x. All right, so I need those e to the x's on one side of this, and I need that negative 5 on the other. And it's up to you which way you go here. We could certainly subtract 5e to the x instead of having to subtract e to the x and then add a 5. We'll get the same answer in the end. So far we have negative 5 equals negative 4e to the x, but I have to isolate and expose that base, which is the e. So I need to divide both sides by negative 4. And now I have to use natural log to solve this. Even though they didn't say to, we have e, the natural base. So to get rid of the natural base, I notice I didn't leave myself enough room here. We're going to take the natural log of each side. And that's because we need an inverse for e. We need an inverse for this base. These are perfect inverses. This is going to give us x, and that'll be much easier to punch in than what we've been doing. So natural log of 5/4. So I don't think I'll show you that one on my big calculator here. I think I'll just tell you that's 0.223 to 3 decimal places. All right, let's go back up. Again, we're supposed to think about using factoring to solve, thinking of quadratic techniques, which would be factoring. Oh, okay. Well, it looks like we should move all that stuff over to one side so we can try and factor. So let's go ahead and subtract. X squared e to the x. Because typically, when we're trying to factor, we'll move everything over to one side because solving means finding the zeros. The first one we didn't necessarily have to do that for, but let's take a look and see what's going to go on here. Using factoring methods. Well, let's see. They both have an x, and they both have an e to the x. So we get x e to the x times the quantity 3 minus x. Double check in here. Took x out, e to the x out. All right. So now what we have to do is we have to find the zeros. And that means x e to the x could be 0. But it also means 3 minus x could be 0. Well, this one's pretty easy to solve. We'll just go ahead and subtract, or actually I'll just add an x to both sides. That'll make that easiest instead of doing it in 2 steps. So we have x equals 3. And then over here, if we're going to solve that, well, we have to figure out how would this come out to be 0? Well, it could be that the x will be 0. That's a possibility because then 0 times everything will give us 0 right here. Also possible that e to the x would come out to 0. Let's think about that one for a second. So if e to the x is supposed to come out to be 0, that means that there's some power that we can raise e to that would give us a 0. Well, that's not going to happen. E to any power is going to give us a number back that's not going to be 0 in there. In fact, it's going to give us positive values. So this one is undefined. But we did get these 2 pieces. So let's go back and see if that would actually work. If we put a 0 in for x, we'll get 0 here, but again, we'd have that e to the 0 piece right up there. So e to the 0 is 1. We should be just fine. It'll be 0 times 0. So e to the x equaling 0, that can't happen. But we can put a 0 in for x, and then e to the 0 is 1. So that works. So this gave us 2 solutions. Now that got me thinking while I was going through this problem. How do you know how many solutions you should get? And it really comes down to the degree again. And when we look at h, it had an x to the first as the exponent. X to the first is linear. We should get 1 solution. And for I, we had an x squared. So that would be a degree 2, which means we should have 2 zeros or 2 solutions. And we're going to focus on that a little bit more as we get into some of the other problems that we have to do today. But it's always good to know how many are we looking for here. Alrighty, so this is a really fun method. Example 1 continued. We're doing a lot with these. Solve the exponential equations algebraically. All right, so I look at J, and the first thing I see is, they left a negative exponent. We can't do that. So this E, because remember, exponents work for the closest thing to their left, that's going to have to go down in the denominator. Oh boy, now we have a denominator. That makes this a rational equation. Well, normally we would multiply by the LCD. We're dividing here by e to the x. That's our LCD. Well, since that's what we normally do, we need to continue that. So we're going to have to multiply each of these terms by e to the x, which again is basically multiplying both sides by e to the x. So what on earth do we do with that? E to the x times e to the x. Well, remember, when you multiply similar bases, you add the exponents, and x plus x is 2x. All right, so now, method. It said use factoring, solving quadratics techniques. Okay, so that would mean I want the squared term first, then I want the x to the first term, and then I want the number. So I will have to subtract 2e to the x from both sides and put these in order. But that gives me a negative in front of my first term. And we know that we're not supposed to leave a negative in front of our first term because then we have a greatest common monomial factor of a negative 1. But that's easy enough to get rid of. We can just divide both sides by negative 1. All right. Now, some people are perfectly fine factoring with e to the x's inside their quadratics. For other people, it freaks them out. So here's what we're going to do. We're going to use a little substitution for just a couple of steps here, and then we'll put it back in. Because it has that e to the x and because that messes with some people, we're going to stop and say, you know what, let's make up a new variable. Let's call w e to the x so that this doesn't look so nasty and everybody can figure out what they need to do. So e to the x, this would be w squared plus 2w minus 3 equals 0. And now it doesn't look so intimidating anymore because that looks like a pretty basic little factoring problem right there. So it's nothing special. We've already taken out the greatest common monomial factor. We just need to do some good old-fashioned factoring and figure out two numbers that multiply to negative 3 and add to 2. So there's our zeros. So normally we would say that our zeros here come from w plus 3 and w minus 1. But remember, I substituted in that e of x just to make it easier to factor. This really says e to the x plus 3 will have to equal 0. And this really says e to the x minus 1 will have to equal 0. But it does make it a little bit easier. So we're going to go ahead and subtract 3 from both sides and add 1 to both sides. Now, we can already see that one of these is going to give us issues. And that's because raising e to some power and getting a negative, we can't raise 2.714 to some power and get a negative. So this one is undefined. Our answer is really going to come from e to the x equals 1. And to solve that one, you could either just think about it for a second, or you could, of course, take the natural log of both sides. E to the something comes out 1. Well, that something has to be 0. That's the only power you can raise it to that would give you 1. So x equals 0. Now, with this problem, it was a quadratic. I mean, pretty obviously we had a squared as we went through here. But when we go back up and look at the original, we realize this was e to the x. This was 1 over e to the x. X to the first is linear. There really should only be one solution. And that is what we found. Took a while to get there, but that's what we found. Now, like I said, some people are perfectly fine factoring with e to the x in there. They just think of it like it's another variable. But for most people, it really helps to do that substitution, and it makes it a lot clearer as you work through the problem. So we're going to do another one of those. So I look at k, and I start thinking, that is super close to what we just did, except they have this dividing by 2 business. Well, then let's multiply both sides by 2, and then it'll look just like the problem we just did. And I see they have that negative exponent, and I know that can't be there. And then I have a rational equation, which means I need an LCD, and I have to multiply them all by the LCD. Pretty obviously, our LCD is e to the x again. So we will get x plus x, e to the 2x, minus, and in the second one, really nice here, the e to the x's drop out, and we get 1, equals 10 e to the x. From the last one and from the method, they told us, use the factoring, the solving quadratics methods. I'm going to have to bring the 10 e to the x over. And then, like I said, you don't have to, but it makes it a lot clearer that we've got these e's in here that are messing up us being able to see what we have to do with this problem. So if we substitute a w in there, and then we can take a look. And in this one especially, you're really glad that you did the w's. And that's because that's not factorable. So when a quadratic is not factorable, we go to completing the square. And if you left that e to the x in there, that's going to be really nasty to keep track of. So much better idea to stop here and say, okay, I've got my w's. Now I'm going to move the 1 over to the other side and complete the square. Well, b over 2 squared would be negative 10 divided by 2 is negative 5, and you square that and we get 25. So now we have the quantity w minus 5 squared equals 26. We'll take the square root of both sides. And we have w minus 5 equals plus or minus the square root of 26. And then we'd add 5. And we would remember, wait a second, I have to put my e to the x back in there. Remember, we only did that so we could solve the quadratic. We only put that w in for e to the x so that we could get to the point where we could solve the quadratic. So it really is e to the x equals 5 plus the square root of 26, and e to the x equals 5 minus the square root of 26. Now, one of these is not going to give us an answer. One of these is going to be undefined. Because again, when we started this, this was an x to the first for our exponents. And that's going to be the one that would give us a negative value. And down here, 5 minus the square root of 26, the square root of 26 is more than 5. So this is going to be negative, and it's undefined. To get the other one, we're going to want to take the natural log. Didn't leave myself a lot of space here. So we'll have natural log of e to the x equals natural log of 5 plus the square root of 26. And natural log and e, inverses of each other, going to cancel right out. And we could very easily punch in the natural log of 5 plus the square root of 26. And there's our answer, 2.312. All right, I'm going to write down this is step 1, step 2, and step 3 on there. So, like I said, you have to figure out how many solutions you're going to have. And as we get to the solving logarithms piece, which it looks like we'll do that tomorrow, we're going to need to know in advance how many solutions we're going to get. So over the last 2 days, we have really hit that first objective hard, which was solving exponential equations algebraically and graphically. Haven't done a lot of graphically yet. Most of this has been solving this algebraically. But we did use the graphing calculator to talk a little bit about the domain and know what's going on with that. But we only have about 3 minutes left, so it'd be kind of silly for me to go on to solving logarithmic equations. And again, that makes me really glad that we did that little piece of this yesterday. If this is in the glare, so you can't see it, can somebody unmute and tell me, then I can try and slide stuff down. All right, you must be okay at that spot then. Reminder, this last test that we take this year, there are no retakes. Tests that are given in the last week of the semester do not have retakes. You've got to get caught up. No procrastinating. Don't try and do 3 or 4 assignments at one time. Get them done each day. That's the way we learn math, little chunks each and every day. But there it is. Have a great day, everybody.